Yellowstone's clock is broken, what scientists are hiding. The gas alarm started screaming first, then the ground monitor ticked upward, half an inch, then more, while a swarm of small quakes rattled the ranger station windows like loose coins. In the control room, someone killed the live feed and picked up a red phone. Across town, a draft memo changed 3 words. Unusual unrest became expected variability. The press line settled on non-event. Behind one locked door, a decision. Hold the new data for review. To understand why anyone would muffle alarms at Yellowstone, we need to go back, before dashboards and press briefings, to the engine under our feet and the rhythm it used to keep. The ancient engine underfoot. Start with a torch that never moves. The North American plate slides, but the hotspot stays, burning a dotted line across states and time. That's the Yellowstone hotspot. Mantle heat welling up, softening crust, feeding a system that breathes in centuries and exhales in moments. Geology books sketch it as arrows and blobs. On the ground, it became 3 stories written in ash and panic. 2 million and change years ago, the Huckleberry Ridge event ripped open the land. Not a cone exploding, but a continent exhaling. Pyroclastic flows racing faster than a car, ash fanning across what would become the Midwest, the sky turning a steel gray that midday sun couldn't punch through. People weren't there to tell it, but if they had been, the first chapter would have been noise. A low, endless freight train roar swallowing valleys. Then the wind would have taken over, sewing glass needles into lungs, making agriculture a memory. The caldera collapsed, a floor dropping, a roof falling in on itself, and the map changed. 1 million years later, a smaller flash. Mesa Falls. Smaller like a hurricane versus a superstorm. Still enough to sandblast forests and make rivers forget their beds. Another caldera scar, another chapter in a hotspot's long handwriting. The pauses between weren't quiet. Rhyolite lavas crept and froze. New geothermal basins boiled to the surface. Groundwater learned new routes through fractured rock. The system rested the way a boxer rests, standing, breathing, never fully still. Then came Lava Creek, about 631,000 years ago, the eruption everyone points to when they talk about the supervolcano. Its ash blanket shows up in drill cores from coast to coast, a thin gray line that geologists pull out with tweezers and a grin, because it's time travel in a smear. That line is a clock tick. It says, this place can build pressure quietly for a very long time and then spend it all at once. Meanwhile, under our later boots and cameras, the plumbing kept evolving. A lower reservoir, deeper, hotter, buoying, less viscous melt, feeds an upper, cooler, crystal-rich body, more a mush than a lake of magma. Between them, cracks in sills and dikes, the capillaries that let heat and gas and melt move. When the valves are partly open, we get geysers, center terraces, sulfur breath on a windy day. When a valve sticks and a seal fails, we get hydrothermal blasts, steam-driven explosions that snap trees like matchsticks and leave craters where tourists took photos last summer. Ask anyone who's hiked before dawn with a field crew. The ancient engine isn't abstract. There's the crunch of brittle center under your boots, the hiss from a vent that wasn't there last week, the sudden metallic taste when wind swings and you realize the gas has changed. More CO2, a sting like rotten eggs turning up in the mix. Someone checks a handheld meter and says, "We don't linger here." They don't have to say why. Out beyond the boardwalks, the record in rock is patient and blunt. In a lab, a thin core spins under a microscope, and a grad student sees shards of volcanic glass, bubbles frozen mid-escape. The ash layers stack like lines of code. They say long dormancy punctuated by fast events. They also say dormancy is not sleep. It's storage, it's assembly, it's heat moving into place. A ranger remembers his first steam blast at Norris. No warning, just a hard call from the ground and a column of gray-white punching up. Nobody got hurt that day. The crater was the size of a pickup. It felt like the system clearing its throat. Later, he learned there's a pattern. Pressure builds in the shallow plumbing. Water flashes to steam. Rock breaks. Small doesn't mean trivial. It means the lid still holds. Now take the map and zoom out to farmland, to grain routes, to power lines strung across plains. The hotspot's plumbing matters because we live downwind and downstream of it. Ash isn't dust, it's microscopic glass. Put enough of it in jet engines and they stall. Put a few millimeters on high voltage insulators in damp air and you get flashovers and blackouts. Put a gray film on a wheat field at the wrong part of the season and yields drop. That's not apocalypse talk, it's logistics. But the past sets more than stakes, it sets expectations. The old rhythm that creeps into public conversation goes like this. 3 huge eruptions with hundreds of thousands of years between them, so the clock must be slow. You can almost hear the comfort in that. The engine's big cycles look like they give us room to breathe. Here's the catch we'll keep coming back to. Those big eruptions were the last pages of long chapters. Between them, the engine kept moving heat, flipping valves, sealing and unsealing pathways. The pauses held action that didn't leave postcard volcanoes, but did leave signals. And when you listen to those signals with today's instruments, GPS pins, satellites feeling the ground rise, seismometers counting the tiniest pops, the rhythm doesn't land where the old clock says it should. We carry that thought forward because it decides what we do with alarms. The ancient engine taught us how it spends pressure. Our gauges tell us how it might be saving it now. The official clock and its blind spots. The old rhythm shows up in headlines as a number, overdue by 70,000 years. It sounds precise, like a train schedule. It comes from averaging 3 big eruptions and subtracting the time since the last one. Simple math, wrong metaphor. Volcanoes don't count evenly spaced beats. They hoard heat and change plumbing until something tips. Even the agencies push back on that myth. They'll say recurrence intervals are not timers. They're right. In fact, with only 3 data points, the average is statistically meaningless for prediction. Some popular retellings say 70,000 years overdue. Others say about 100,000 years to go. Both miss the point. There is no countdown clock. But the comfort lingers because a slow clock is easier to live with than a twitchy one. So the official clock leans on what can be measured and averaged. The monitoring pillars are the pendulum. GPS monuments cemented into bedrock, tracking millimeters of uplift or subsidence. INSAR satellites watching the caldera breathe from orbit, stacking images into color bands that reveal bulges and sags. Seismometers listening for microquakes most people never feel, the tiny breaks and slips as fluids and rock adjust. Gas stations sniffing CO2, helium ratios, the sulfur that betrays fresh magma if it reaches the surface. Rangers and geologists logging hydrothermal behavior, pools clearing or clouding, vents migrating, geysers changing intervals. The models that sit behind those instruments were built in an era of patience. They weight long repose times heavily and assume recharge that behaves like a slow IV drip. If the ground is rising a few centimeters a year and the gas looks mostly like old water boiling, the model calls it background variability. If swarms come and go without strong low-frequency events, the model nods. Normal for a restless hydrothermal system. The public line follows the model. No eruption imminent, variability expected. But there's a blind spot baked into that comfort. It shows up in the rocks, not the reports. Magma at Yellowstone isn't a single vat. It's a spectrum from crystal-rich mush to hotter, more mobile melt. The difference between a quiet mush and an eruptible pocket can be a small thermal push or a pressure change that melts the ice between crystals. Crystal clocks, zircon and feldspar, capture that. They record episodes when heat surged and mush flipped to melt in decades to centuries. Not glacial time, human time. Comparable decadal scale remobilization has been inferred at other caldera systems, which is why averages don't forecast behavior here. Meanwhile, models that treat melt as a single velocity fluid miss what happens when different domains couple. A dike injection at depth can connect compartments and fluids, CO2-rich first, outrun the melt, pressurizing shallower zones, changing seismic patterns and gas without obvious sulfur. The hydrothermal system acts like a shock absorber until it doesn't. The official pendulum watches averages. The system moves in bursts. A scientist told me how that plays at a conference. She had a slide. GPS curves from 2004 to 2001, then the later pulses with short, sharp uplift bursts circled. Her note under the figure said, rate changes incompatible with pure hydrothermal forcing. The night before the talk, during a prep call, a senior voice suggested a softer phrase, consistent with known variability. She changed it. Later, over coffee, she shrugged. Words matter, she said. So do grants. She didn't sound bitter, just tired. What nobody knew in real time during those pulses was how patchy the ground moved. The caldera center rising while the edges sagged, then flipping, dome versus basin, asynchronous, like a heart with a skipped beat. The model flagged it as expected, breathing. But there was one detail that stuck: the short, sharp bursts. They arrived faster than seasonal snowmelt artifacts, too broad to be a single geyser basin pressurizing. They suggested intrusions, thin sheets of magma or hot fluids wedging in then stalling. If you live anywhere downwind, Denver, Billings, Rapid City, Omaha, even Chicago on the wrong week of wind, these patterns aren't trivia. They're the early moves that, if they cascade, decide whether planes fly, grid gear stays clean, and food prices don't jump next season. Here's where the blind spot tightens. The sulfur puzzle becomes an excuse. No SO2, no fresh magma, the line goes. Except sulfur scrubs easily in a wet, capped system. It dissolves into water and binds in rock before it sees daylight. CO2 and helium ratios are harder to hide, and they started whispering mantle fingerprints in expanding degassing fields. The official clock, tuned to sulfur, missed the new fuel signal. Another meeting, another memo. An interagency call wrestled with a word: unrest or variability. Unrest trips thresholds. Tourism boards get antsy. Emergency managers ask for money. Variability maintains calm and keeps the phones quiet. The compromise was a bland paragraph and a promise of ongoing review. In the same hour, a flight to sample gases over a northern basin was postponed for internal quality control. The pilot put a question mark next to the date on his log and didn't erase it for 3 months. From a distance, all this looks like caution. Up close, it feels like drift. The clock is slow until it's not, and language keeps it slow. The instruments are good, the people are careful, but the framework lags the physics. Multi-velocity magma, mush-to-melt switches, rapid mobilization. Those aren't fringe ideas, they're the current literature. The official pendulum hasn't caught up. While models sleep, the ground started moving differently. And in the next beat, something else began to speak. Gases rising through cracks that didn't exist a decade ago, hinting at plumbing the old clock never timed. The uplift that wouldn't behave. Start with a curve that doesn't care about explanations. In late 2004, the caldera floor began to rise. Broad, steady, undeniable. GPS pins at White Lake and Sour Creek drifted upward like someone was cranking a hidden jack. Over the next years, through 2009, the whole bowl lifted tens of centimeters. The official line called it caldera breathing. Inside field trucks, the word was simpler. It's moving. If that pulse had been the whole story, the model might have survived untouched. But the ground didn't keep one rhythm. After the big rise, it eased, then subsided, then rose again. Shorter pulses nested inside the longer trend. The strange part wasn't just up versus down, it was where. The two main domes, Mallard Lake on the southwest, Sour Creek on the northeast, took turns bulging while the other side. 1 month, the northeast swelled like a slow tide while the southwest flattened. Then the pattern flipped. It looked less like a chest breathing and more like plates shifting under a tablecloth. That asymmetry matters. A hydrothermal system can pressurize, sure, but it tends to show its hand locally. Basins puffing, vents hissing, a boardwalk buckling here and there. These were basin-scale moves, tens of kilometers across, too broad for a single steam field, too asynchronous for a uniform aquifer cycle. They pointed to intrusions, thin tongues of hot material wedging into mush zones, rather than just water flashing to steam. Meanwhile, satellites watching from orbit painted the same odd picture in color bands. Interferograms stacked over months showed concentric rings that didn't share centers. One bulge here, a sag there, then a new lobe swelling off-axis like a bruise migrating under skin. The timing didn't line up cleanly with snowmelt or lake level changes. Analysts tried to clip out seasonal noise. The bursts remained. Those short, sharp bursts kept coming back. A GPS monument would tick upward a few millimeters in days, pause, then slide a hair, repeat. Too fast for deep crustal flexure, too coherent to blame on one frozen sensor. In meeting rooms, the phrase episodic intrusion started to appear in the margins. Not a continuous pressurization, but pulses. Dikes or sills squeezing in, stalling, degassing, maybe cooling, then another pulse. The hydrothermal hypothesis fought back. Yellowstone's shallow plumbing can seize and relax in days, that's true. But if steam alone were the driver, you'd expect stronger synchronized signals in the nearest geyser basins. Sudden changes in intervals, water chemistry flipping, new blowouts aligned with the deformation lobes. Some of that showed up, but not with the right cadence. The ground seemed to get the memo before the basins did. A field micro story. A summer tech named Lila babysat a GPS site near the Sour Creek Dome. She hiked in every week with a toolkit and a thermos, cleared snow from the solar panels in spring, shooed bison in July. In September, her receiver logged a 2-day jump, 5 millimeters up, 1 east, clean, no multipath. She sent a note. The reply was a template about seasonal effects. She taped the plot inside her trailer. Anyway, when the same 2-day hop appeared at a station 20 kilometers away a month later, she circled both in red and wrote, "Buddy system" on the printout. It became a quiet joke until it didn't feel like one. Dome versus basin dynamics tell you something else. The system isn't a single balloon. It's a stack of cushions with leaks and clamps. When the upper reservoir takes a pulse of heat or gas, it can swell where the mush is primed. Warmer, wetter, crystals less interlocked. Another patch might sag as fluids escape along a fault. Pressure bled off before it can lift rock. You end up with asynchronous teeter-totters instead of a tidy inhale-exhale. Seismology added texture. During some uplifts, small swarms trace lines at the edges of the domes, little brittle pops sketching possible intrusions, then going quiet. Low-frequency tremor, the kind that hints at fluid movement, flickered more under Norris and West Thumb than directly above the biggest bulges, as if the pressure wave was rerouting through old fractures. If magma was a messenger, hydrothermal zones were its gossip chain. Through all this, one argument kept resurfacing. Rate matters. A centimeter a year is one thing, a centimeter in a week is another. The first suggests deep, slow forcing. The second hints at something mobile. Rate changes, accelerations, and sharp stops are how you spot a valve being opened or a seal wedging in. The official summaries liked cumulative maps. People in the field watched derivatives, the slope of the slope. And then there's the silence of sulfur. During several uplift spells, SO2 at the surface stayed low. That fed the steam-only camp. But look at CO2 flux surveys laid across meadows over those same months. Patches of high emissions spreading, tree roots suffocating in new dead zones. Look at helium isotopes drifting slightly toward mantle signatures. Those signals arrive early and travel far. Sulfur gets scrubbed, carbon slips through. What this all implies is uncomfortable and practical. If the deformation is driven, even partly, by episodic intrusions coupling to a patchy mush, then the system's response time isn't glacial. It's immediate. A thin dike can move in days. A shallow seal can fail in an afternoon. The difference between "we'll know centuries ahead" and "we'll know after lunch" is in the rates, the asynchrony, and the coupling we see on these curves. Ground moves slow, people say. True, until it doesn't. In Yellowstone, the ground started moving like a conversation. Call and response across domes, interrupted sentences, sudden emphasis. That's not how a clock breathes. It's how a system negotiates new plumbing under pressure. Gas whispers from below. If the ground is the body language, the gases are the breath. Quiet, warm, and full of clues. Start with carbon. CO2 seeps out of Yellowstone year-round, but the pattern has been changing. Survey teams laying plastic chambers over meadow soils kept finding bigger hotspots. Patches that weren't there on older maps, where meters tick up and tree roots brown from strangled oxygen. On cool mornings, you can see it in the way fog hangs odd in low spots, thicker than it should be. A ranger calls it ghost air. The chemistry calls it an expanding, diffuse, degassing field. The ratios matter more than the totals. Helium has flavors. Most of what we breathe is crustal, but a small share, helium-3, carries a mantle signature. When the 3/4 ratio nudges upward, even a little, it's a fingerprint of deeper input. In several basins, those ratios bent toward mantle values at the same time CO2 flux grew. That pairing is hard to blame on boiling old groundwater. It says the system isn't just exhaling yesterday's steam. Something fresh is pushing from below. Then there's sulfur's quiet. People expect to smell rotten eggs if magma climbs. In a dry, open system, you would. Yellowstone is neither. It's wet, fractured, and capped. SO2 dissolves into water, reacts into sulfate, gets trapped before it reaches the sky. So when the official line leans on no sulfur spike, they're trusting a break that's built to hold, until it doesn't. Meanwhile, carbon slips through early, faster, farther. If you want the early whisper, you listen for CO2 and helium, not the shout of sulfur. Microstories accumulate. A hydrologist sampling the fire hole noticed the river's dissolved inorganic carbon jumping a few percent above its usual swing, right as an upstream meadow's CO2 flux map added new red pixels. The same week, a cottonwood stand at the edge of that meadow yellowed from the bottom up, a classic suffocation pattern. In her field book, she wrote 2 words underlined twice: fresh input. Another, a pilot with a nose for thermals flies a fixed-wing pattern over West Thumb to chase down a routine gas transect. 2 hours before takeoff, the run is paused for internal review. It's not the first time. He logs the cancellation, adds a question mark, and goes home. 3 weeks later, the same. Transect gets a green light, but by then the wind patterns have shifted and the lake's thermal skin has cooled. The data are clean. They're also late. Gas doesn't move alone. It drags water chemistry along. In the Madison River, a summer profile picks up slight increases in bicarbonate and a trace of chloride where a cold tributary should have diluted everything. Not a headline, but a nudge. The lab report's footnote mentions isotopes trending toward magmatic CO2. Small but coherent, the analyst writes. That phrase keeps showing up. Meanwhile, trees tell their own version. At Norris and near the North Rim, foresters flag new mortality patches, irregular ovals where conifers browned in clumps. Soil probes beneath them read high CO2. The pattern spread downslope over a couple seasons, not with beetle galleries or drought stress, but with invisible gas pooling in hollows on still nights. The park's botanist filed it as physiological stress likely due to soil gas. The volcanologist filed the map. The absence of sulfur remains the puzzle that comforts. It shouldn't. At Campi Flegrei and Rabaul, similar wet caps muted SO2 until systems unzipped and the signal jumped from silence to scream. Yellowstone's cap is broader and colder, a champion sulfur scrubber. If you're waiting on that scent to declare fresh magma, you'll be late by definition. Then there's a detail most visitors miss: bubble size. In a few pools that used to simmer gently, bubbles grew fatter and fewer, classic CO2-rich degassing. Boiling water makes chains of tiny, frantic pearls. Carbon makes heavy beads that pop with a soft thud. A tech at West Thumb filmed it, slow motion, and laughed in the lab. "It's like the system switched soda brands," she said. Her supervisor nodded, then added the clip to a training deck on gas signatures. All these threads, ratios, rivers, roots, bubbles, point in the same direction. Renewed input from below, not just old water finding a new crack. The timeline attached to that is the part that bites gases outrun magma. CO2 can be the first postcard from an intrusion we won't see on a satellite for months. That's why canceled flights and delayed field runs matter. The early signal is perishable. Impact lands quietly. The more domains that light up, meadows, river chemistry, isotope ratios, the tighter the plumbing feels. Pressure couples faster. Hydrothermal caps stiffen, then creak. Valves that held for decades start to chatter. If gas says new fuel, it's telling you the engine's throttle just opened a notch. And if that's true, the next voice that rises won't be a whisper. It will be the map of tiny earthquakes learning new routes through rock. The swarms that drew a map. If gases are the whisper, swarms are the handwriting. Messy loops that keep returning to the same alphabet. Yellowstone's earthquakes aren't the cinematic kind. They come in clusters, hundreds of tiny taps that migrate like a slow scribble across a desk. On a quiet week, analysts see scattered pops. On an interesting week, the dots connect into lines that drift, stall, and turn, like someone testing doors in a dark hallway. This isn't a tomorrow problem, but it is a this decade decision problem. How we read these lines now sets what we can protect later. West Thumb does one kind of anger. Under the lake's cold skin, low-frequency events gather in bunches. Soft thuds more than snaps, stacking at depths that match hydrothermal vents on the lake floor. When these pulses come, hydrophones pick up a faint, bassy tremor, as if the basin is humming to itself. Boiling? Maybe. But those events sometimes step outward along a known fault, and their spacing looks tidy, meters apart, seconds between, like fluid pushing through a zipper. That's a pattern you see when gas finds a new seam. Madison Valley has a shorter fuse. Its swarms tend to be brittle and hurried. Sharp microquakes marching along northwest lines that echo old breaks in the crust. They start compact, then fan, then go silent, the way a dike might test a rock and back off. You can overlay 3 years of these and watch a ghostly ladder lean against the caldera's edge. Norris is the one people watch with a hand on the door. Its swarms come layered, high-frequency cracks at shallow depth. Then hours later, a faint roll deeper down that doesn't show up in the first filter. The timing feels like a pressure wave arriving late. In the days after, small vents migrate, a pool turns milky, and a trail closure sign appears with a polite tone that doesn't quite hide the urgency. Norris is a governor on the system. When it stiffens, everyone pays attention. These aren't isolated pots. Over a few seasons, the swarms outline connections. A run at West Thumb would fade just as Madison lit up. 2 days later, Norris would answer with a low, even murmur. It looked like a pulse moving through a network. Deep input pressure rises under the lake, fails to break there, tracks along the ring fault toward Madison's fractures, bleeds, then sends a longer wave toward Norris's cap. Earthquakes drew that map before any press release framed it. A night shift analyst named Ramon heard it first. He was new enough to still be excited by cataloging, old enough to trust his ear. At 2:13 a.m., a stack of small events under West Thumb started to repeat, a beat with a little swing. He pulled a spectrogram, saw energy drift from 1 to 3 hertz in a stair-step pattern, and pinned the window. An hour later, a similar stair-step appeared under Madison, phase shifted, a hair tighter. He marked that too. By dawn, Norris was printing a soft, long-period tremor that matched the same slope. He slid his chair back and said to the empty room, "It's talking to itself." In the morning meeting, the note went into the log. It didn't change the summary, it changed how a few people listened. Low-frequency events sit at the center of the argument. They can be boiling in fractures, magma moving, or both. In a place as wet as Yellowstone, separating water from melt is a headache. But when you get migrating swarms that follow a fault trace, show a clear progression of depths, and end with gas anomalies or a pond's chemistry flicking toward chloride, you start leaning away from just steam. Fluids are moving. Some days, the fluids carry the signature of new heat. The migration speed matters. Dikes advance at meters per minute to meters per hour. Hydrothermal fronts move slower. Yellowstone swarm trains often creep at rates that sit between too fast for pure pore pressure diffusion, too slow for a clean dike racing. That middle lane is the coupled case. Gas-rich fluids leading the way, fracture tips preparing space, melt staying back but sending pressure forward. By the time magma faces decide whether to follow, the hydrothermal system has already adjusted, sealed some cracks, blown others, and left a breadcrumb trail in quake times. Patterns repeat. Summer 2008 drew a diagonal from West Thumb to Madison in 3 days, with Norris humming on day 5. Winter 2017 did the same run shorter and tighter, capped by a small hydrothermal blast near Emerald Spring that never made cable moves. In both cases, CO2 meters in meadows along the line ticked up in the week after. That's not a coincidence. That's plumbing. One detail that unsettles field crews: swarm density spikes right before rate changes in the ground. The 2-day GPS hops from Section 3 often land on the back of a 12 to 24-hour period where tiny events pile up like sleet. Then the swarms go quiet as the ground takes the step. It feels like a head fake, but it's the opposite. The brittle crust protests, then yields, then rests. Watching that. Cadence turns swarms from noise into timing marks. None of this says tomorrow, it says connected. The old picture of isolated basins, Norris as its own beast, West Thumb doing lake things, Madison doing fault things, misses the way pressure finds paths. The swarms drew a map of valves and hallways. They also taught a hard lesson. The system can reroute fast. An intrusion that fails under the lake can show up at a hillside vent 2 days later, and the only hint in between is a staircase of low rumbles most people sleep through. Impact is simple. A connected system couples signals. Rate changes in ground deformation, gas whispers in meadows, and migrating swarms start to land closer together in time. When that happens, your warning window narrows. The map that swarms drew isn't just a diagram. It's a stopwatch with jagged edges, and it pointed to the next reveal. Rocks cooled long ago, telling us the clock doesn't tick the way we were taught. The 20-year recharge surprise. Rocks that cooled 100,000 years ago shouldn't have anything urgent to say. Then geochemists started cutting them thin and timing the crystals inside like stopwatches. Zircon and feldspar don't lie about heat. They grow when melt is present, they stop when it cools, and the diffusion profiles along their rims keep a memory of the last warm breath that touched them. In lab rooms that smell like ethanol and patience, those profiles started whispering something awkward. Assembly can be fast. Not geologic fast. Decades fast. You can almost smell the lab air, acetone, warm instruments, while a laser walks a rim that records a few hot years that changed everything inside the mush. Here's how the clocks work. Zircon likes hot, silica-rich melt. When a reservoir heats up, new zircon grows, and its uranium lead age pins when the melt was eruptible. Feldspar, loaded with elements that move at known rates, records how long it sat at certain temperatures before the system changed. Put enough crystals on a spreadsheet and you can map pulses of heat. At other calderas, Rabaul in Papua New Guinea, Campi Flegrei near Naples, those pulses lined up tight against eruptive episodes. The kicker wasn't the explosion, it was the ramp. Crystals saw decades of rejuvenation before events that changed skylines. Picture a diffusion profile like tree rings squeezed near the bark, tight bands that only form if the last warm-up was short and intense. Yellowstone's crystals got the same treatment. Old studies assumed long, steady storage. New work reread the rims and diffusion halos and saw spikes, narrow bands where elements migrated over distances you only get if the melt got hot and stayed hot for years to tens of years, not millennia. The zircon ages clustered suspiciously close to known lava and ash units. The feldspar zoning said the mush wasn't just a pantry, it was a kitchen that could be turned on quickly. Call it the mush problem, flipped. In a big silicic system, most of the volume is a crystal network with melt threaded between grains, like snow with slush in between. That mush is stable until you add heat or volatiles. A small intrusion from below, a few percent by volume, can raise temperature a handful of degrees, lower the melt's viscosity, and suddenly the grains are swimming, not locked. That's the switch. You don't need a fresh ocean of magma, you need a thermostat nudge. The crystals record that nudge as a sharp-edged zone you can measure with a laser. A case study helps. At Rabaul, the 1994 eruption followed about 2 decades of unrest, uplift, gas, and quakes that looked annoyingly like background until it wasn't. Zircon rim ages and diffusion models later showed a rapid assembly window in the decades prior. Campi Flegrei's recent decades of Bradyseism, slow rise and fall, come with geochemical hints of quick remobilization episodes. Yellowstone isn't Naples. It shares the physics. Reinterpreting Yellowstone's crystal data doesn't predict a date, it shrinks a category. Recharge used to mean thousands of years of steady drips filling a bathtub. Now it can mean years to decades of pulses turning a slushy bowl into something that can move. Couple that with the deformation bursts and the gas ratios we've been hearing, and the timeline stops feeling like inheritance and starts feeling like planning. A micro story from a lab bench. A grad student named Kieran was running secondary ion mass spectrometry on zircon from a late rhyolite flow. He kept getting rim ages bunched within a human lifetime before the eruption, the kind of clustering you expect in basalt, not in a giant silicic system. He reran standards, checked for lead loss, swore at the machine, then sent the plots to his advisor with a subject line that read, "Please tell me I'm wrong." The reply arrived an hour later. "You're not. Start writing." This is the part that unsettles meetings. If mush can flip to mobile on decadal scales, your hazard frame moves into policy time. Lifetimes.
Infrastructure cycles. Insurance windows. It means we'll know centuries ahead. Comfort collapses into we'll see coherent signs and have to choose within the span of a career. It also means you can miss the window if you only watch for sulfur and cones. There's another twist. The first phase of that switch is quiet at the surface. Heat and volatiles percolate up. CO2 takes the early train, helium ratios lean deeper, deformation rates stutter, swarms migrate. SO2 stays scrubbed. The crystal clocks are telling you what the system did last time it got ready. Our instruments are telling you it knows how to do it again quickly. Skeptics point out the obvious. Yellowstone has been restless without erupting for a long time. True. But the question isn't, will it erupt tomorrow? It's, how fast can it build the conditions to? Decade-scale assembly fits inside a human spreadsheet. It also fits uncomfortably well with uplift pulses that move in days, gas fields that expand over seasons, and swarms that draw new hallways in weeks. So who manages the throttle if the engine can spool fast? That's the political question we'll get to. The scientific one lands first. Stop treating recharge as a glacier. Treat it as weather. When the crystal clocks and the present signals rhyme, you don't count from the last big blast. You start a new timer and admit it might be set in years, not eons. The meetings, memos, and messaging. It starts in rooms with bad coffee and good intentions. Tuesday, 9 a.m., an interagency call that always runs long. Evo scientists, park leadership, state emergency managers, a tourism liaison who keeps reminding everyone about peak season optics. The first slide is the dashboard we've been living with. Uplift curves, swarm counts, gas ratios with cautious error bars. The second slide is language, unrest or variability. Someone says unrest triggers policy thresholds. Someone else says the data don't meet the bar. The volcanologist at the end of the table stares at her notepad and draws two circles, one labeled physics, one labeled phones. The tension has three roots: scientific uncertainty, no one wants to cry wolf; political pressure, don't spook bookings; and budget constraints. Wording can tilt grants and overtime. The phrasing battles never look dramatic from the outside. They land as footnotes, consistent with past variability. No immediate hazard indicated, ongoing evaluation. Inside the room, the edges are sharper. A seismologist points to short, sharp rate changes on a GPS plot and says, "This is not seasonal." A hydrothermal specialist counters, "It can still be hydrothermal." The emergency manager asks a practical question. If I use the word unrest, what happens next? Phones, budgets, headlines, those are the aftershocks. Grant cycles hum in the background like an air conditioner. You only notice when it shuts off. A junior researcher practicing her briefing is told to avoid rapid mobilization unless she can anchor it to a peer-reviewed study in the last 2 years. She can. The supervisor nods, then suggests swapping in recently recognized processes. It's not just caution, it's survival. Soft language travels farther without setting off alarms in offices that hold purse strings. This is how a cushion becomes, to outsiders, a cover-up. The mix of caution, politics, and budgets sands off edges the public should sometimes see. Tourism boards sit at the edge of these calls, sometimes silent, sometimes not. A county official clears his throat and says a bureau is fielding cancellation emails after a blog ran unrest in a headline. "We need to balance accuracy with community impact," he says. He's not wrong. His town's winter business depends on the kind of calm that melts easily. A ranger who spends nights near Norris hears that and thinks about the pressure gauge that jumped last week and the trail closure she posted with a smile. Then there's the data that doesn't land when it should. A request goes up to embargo, a new gas transect, pending quality control. The internal justification: calibrations drifted on a sensor during last month's storm. The ratios need a second lab to confirm. The external impact: no numbers in the next update. A field team grinds teeth because the patterns are clear, even without a second decimal place. CO2 is expanding into meadows where it didn't pool before. Helium ratios aren't shrugging off the mantle nudge, but the memo says defer, and defer buys peace in inboxes. Call the driver what it is: institutional caution reinforced by political optics and budget fear. A resignation letter circulates in draft, never sent. The author is mid-career, tired of sentence surgery. She writes that risk communication has been bent by non-scientific incentives, then deletes the line and saves the file as notes. She stays. Most do. They still file the sharp plots in internal folders with names like "Watch Later." A micro story from a hallway, after 1. Call: an analyst corners his boss with a printout of a swarm spectrogram. The staircase Ramon heard. "If we say variability again, we're going to train the public to ignore cadence," he says. The boss rubs his eyes. "We can say variability trending atypical," he offers. It's a compromise that tastes like lukewarm coffee. The analyst adds a footnote in the monthly blog anyway. Rate changes matter. It survives copy edit. The victory is small and real. Pressure doesn't just build underground. A state senator phones the observatory and asks for a briefing to prevent panic. The meeting slides get one new bullet: no evidence of imminent eruption. It's true, and it becomes the headline, quote. The part about episodic intrusions and decadal assembly stays in the second paragraph that most readers don't finish. A local paper runs with all normal. A podcast cuts the caveats and posts, "Scientists say calm down." Clicks run their course. The people inside the machine aren't villains. They're triaging attention. A comms officer drafts 2 versions of an update, one with unrest, one with variability. She knows which one will go up. She also knows she can slip in a graph that shows acceleration, not just totals. The caption is careful, the picture is not. It's a quiet rebellion in pixels. All of this matters because the clock we've built is made of words as much as instruments. If you call a burst variability 5 times in a row, The sixth time, your warning sounds like a rerun. If you embargo early whispers in the name of polish, you give up the lead that carbon buys you. The physics isn't paused by phrasing. The audience is. So we name the forces plainly: uncertainty, politics, and budgets. And then we design around them. Strip the spin, and the signal's still there. Rate changes, migrating swarms, gas ratios leaning deep. The next rooms on our tour won't have memos. They'll have maps of reservoirs and conduits and thresholds that don't care about grant cycles. That's where we go now. Past the language, into the magma. 2 chambers, 1 problem. Strip the slides down to the bones and you get this. 2 reservoirs stacked like lungs, breathing through a chest wrapped in fractures. The lower one sits deep, hotter, bigger, fed by the hot spot's constant heat. It isn't a vat of syrupy magma. It's a sponge of crystals soaked with melt, hotter than anything above. The upper one, closer to the surface, is cooler and stickier, a crystal-rich mush that's most of the time too locked to move. Between them, a messy web of sills, dikes, and faults, the hallways that decide where pressure goes when something nudges the system. Seismic tomography gave us the first honest shapes. Geophysicists fired waves through Yellowstone and listened for the slow patches, zones where seismic energy dragged because hot, partially molten rock smothered the signal. Early images looked like cloudy puzzles. Newer arrays sharpened the picture into 2 broad, low-velocity bodies, a deeper, thicker reservoir and a shallower, patchier one. Then came the hard translation. Melt percent in those images isn't a lake of liquid. It's the fraction of liquid between crystals. 10 to 20% melt can be mobile if you warm it a bit. 30% can act like a slurry. At 40, you've crossed a threshold where rock starts to behave like a fluid, if pressure helps. That's where thresholds matter more than averages. Yellowstone's upper reservoir doesn't need to be a swimming pool to be dangerous. It needs connected pathways of melt, what petrologists call permeability, and enough gas exsolving to push. Heat from below raises temperature a few degrees. CO2 and water coming up lower the melt's viscosity. Suddenly, the network that was jammed yesterday can reorganize into channels. The lower reservoir, with its steadier heat and larger volume, is the engine room. When it surges, by injection or by a broader thermal pulse, the upper mush feels it immediately in patches that were already close to mobile. Connectivity is the part that never makes headlines. Conduits don't care about our park boundaries. They follow weaknesses. Ring faults from old caldera collapses, pre-existing fractures from ancient earthquakes, the edges where rhyolite flows cooled and cracked. Overpressure doesn't pick a random exit. It finds these pathways, often the same ones swarms traced and gases favored. That's why Norris keeps answering pulses from elsewhere, and why West Thumb's low rumbles sometimes end with a crack opening in a dry meadow miles away. The system's plumbing isn't a tree with clean branches. It's ivy, spreading until it meets daylight. Thermal budgets turned this from a map into a timer. 30 years ago, heat flow estimates already marked Yellowstone as one of the hottest places on the continent. Since then, measured CO2 output, expanding diffuse degassing, and the persistence of uplift signals tell you the engine hasn't idled. Add small episodic intrusions from the lower reservoir, and you're feeding the upper system in bursts. Those bursts don't have to add much volume. They add the right calories and gas at the right time. It's like taking a slushy cup and pouring in a shot of hot syrup. You don't change the cup size, you change the slush's behavior. Numbers help, carefully. Suppose the upper reservoir in places sits at roughly 50 to 65% crystals, with 35 to 50% melt in interstices and lenses. Most of that is locked by geometry until slight warming and gas exsolution reduce friction. A few percent increase in melt connectivity can flip behavior from rubbery to flowing. That tipping isn't linear, it's a door. Seismology sees it as changing attenuation. Deformation sees it as faster, sharper pulses. Gas sees it as more efficient escape, more CO2 for the same deep input. None of these alone prove the door opened. Together, they lean on it. Meanwhile, the conduits plan the headlines. Old collapse faults, especially along the caldera rim, are pressure valves. Sills emplaced along bedding planes can delaminate rock sheets and eventually coalesce into feeders. Narrow dikes test vertical routes. Most fail and freeze. Some connect and prime a future path. The first thing that fails in a system like this isn't a city. It's a seal. A caprock saturated with hydrothermal minerals can hold back fluids until heat and gas undermine its strength. When it pops, you get hydrothermal blowouts. Small, loud, and tempting to dismiss. But those are the throat clears along the likely exits. Thermal input today versus the 199s matters, because thresholds crossed quietly don't announce themselves. If the lower reservoir's contribution, heat and volatiles, has inched up, and the upper mush's melt connectivity has crept toward that door, then the same pressure pulse that did nothing 20 years ago can cause a measurable lurch now. That's how people in the field talk about system stiffness. A stiffer system stores more, a softened one transmits. Stakes then are about timing. The moment the upper reservoir behaves as eruptible in zones, meaning melt is connected and gas can push, you've entered a regime where small perturbations have big effects. A modest intrusion becomes a big deformation step. A small seal failure triggers a cascade of hydrothermal responses. The conduits that have been quietly rehearsing become the stage. And all of it happens in a framework that our older models underestimated, because they average what thresholds compress. This is the one problem part. Two reservoirs, two behaviors, shared plumbing. When they couple tightly, slow clocks wobble. When thresholds sit close, language can't buy you time. The system doesn't need a brand new ocean of magma, it needs a nudge along pathways we've already mapped by accident to move from storing to moving.
What actually fails first? The first thing that goes isn't a skyline, it's a lid. In a wet, capped system like Yellowstone, pressure finds the weakest seal, a clay-cemented layer, a center-crusted terrace, a caprock threaded with quartz veins, and it prees. When it lets go, the blast isn't lava. It's water turned to steam in a violent instant. Hydrothermal blowouts are the system's first public failures. They're fast, loud, and small enough to ignore if you want to. You shouldn't. Think about Norris as a case study. Its hydrothermal skin is a patchwork of sealed pores and brittle seams. Pressurize that skin from below with CO2-rich fluids, warm it a few degrees, and the effective strength drops. The fracture network connects, water flashes to steam, and a shallow plug launches. Mud, rock, and boiling slurry. No incandescent glow, no ash column to the stratosphere. But beneath that cough is a message. The shallow lid couldn't carry the load that day. Phreatic versus magmatic is the line everyone wants in real time. You can tell, but the clues are subtle. Phreatic blasts carry old rock fragments with no juvenile glass, no fresh melt shards. Their gases are dominated by steam and reworked carbon. Magmatic events spit glassy ash, crystals with pristine rims, and gases that include SO2, even in a scrubby system. The problem is timing. Field teams don't get microscope slides at the crater rim while the mud's still hot. You read proxies, thermal cams, gas sniffers, and the sound the ground makes when it breaks. Before a phreatic blast, you often see shallow seismic chatter, high-frequency cracks in a tight cluster, paired with a local tilt change as a pocket balloons. Temperatures at nearby pools can drop as water drains to feed the flashing zone. In a magmatic push, you'll hear deeper long-period events, stacking first, tilt meters farther afield trending coherently, and CO2 rising across a broader area. In both cases, SO2 is late or absent until seals shred. That's why waiting for sulfur is a trap. Groundwater is the unsung actor. It can be a lid, a cushion, or a fuse. A saturated caprock stores energy cheaply. Every degree of warming is potential expansion. As volatiles exhale from rising fluids, bubbles form, coalesce, and jam in pores. The pressure rises until the cap yields. The moment it pops, the drop in confining pressure flashes remaining water to steam, adding a runaway kick. That's what turns a hiss into a crater. Field stories sketch the human edge. A crew at Norris closes a boardwalk after a pool goes milky, and a sulfur smell edges metallic. They hang a rope, write thermal change, area closed, and hear the complaint before lunch. That evening, a vent 60 meters off-trail coughs once, then punches a muddy plume 15 meters high. The crater is small, the radius littered with wet gravel. The next morning, a drone shot shows new hairline cracks walking toward a trail. Nobody quotes phase diagrams. They move the rope. Not every blowout is a countdown, but sequences matter. A cluster of phreatic blasts that progresses along a mapped fracture, paired with small migrating swarms and short, sharp deformation steps, is the system clearing pressure along preferred exits. It's a relief, but it's also a rehearsal. Each blast roughens the path, removes sealing minerals, and makes the next failure easier. Steam wins this round. The next round might include gas-rich melt pushing into those newly opened corridors. Geysers that never came back are the quiet archive of these failures. An eruption rearranges the shallow plumbing, and some conduits don't reseal.
A famous cone goes erratic, then silent, because its pressure head bled into a new fracture that now whispers CO2 at night. Park maps don't mark that, longtime observers do. A lost geyser is often a permanent change in how the lid holds. Caprock chemistry sets a clock you can't see. Silica and clays precipitate to seal fractures when fluids are cool and slow. Heat them, add CO2, and the glue softens. Even without a dramatic blast, you get micro-failures that propagate like zipper teeth. Tilt meters near these zones tick in small, stepwise jumps. Seismometers hear the crackle. Gas samplers smell the drift. The headline remains normal variability. The subhead, if anyone wrote it, would read, lid weakening. Impact shows up in closures and maps before it hits the news. A basin posts more area closed, signs in a season than in the previous 5 years combined. A new thermal area forms in a forest patch that used to hold snow well into June. Trees there, brown and ovals, another diffuse, degassing field added to a layer cake of evidence. None of it screams eruption. All of it says the system is transferring pressure through shallow plumbing more efficiently than before. When it isn't small anymore, the timeline compresses. If hydrothermal lids are failing in sequence and deep inputs continue, the next phase isn't guaranteed lava, it's coupled behavior. Long period.
Quakes stack faster. Tilt meters swing in hours, not weeks. Roadbeds heave as frost-jacked fractures get a new warm nudge. Lakes develop odd seiches on windless days. The difference between a phreatic season and a magmatic crisis is the breadth and coherence of those signs. And if you've trained your audience to hear variability, you'll need stronger words on a shorter fuse. This is why what fails first matters. Not because steam craters threaten the continent, but because they mark which doors are opening, which seals are tired, and where pressure prefers to travel. They're the throat clears before a speech you hope never gets delivered. Watching them as noise buys comfort. Reading them as sequence buys time. The compressed countdown. There's a point where background noise turns into music, and you can't pretend it's random. In a fast-coupled system like Yellowstone, that pivot can happen in weeks, then days. The early tells don't look cinematic. They stack. Long-period quakes that used to appear as lonely notes start arriving in tight families. Tilt meters that drifted in lazy arcs begin to write angles, clean, abrupt steps you can match across stations separated by tens of kilometers. Analysts stop speaking in months. They start speaking in shifts. Rate is the tyrant here. You don't just count events, you watch their tempo change. A modest swarm becomes a migrating train that accelerates, pauses, then accelerates again along a familiar fault trace. Overnight, the deformation slope doubles and stays doubled. What looked like spasms now looks like a pulse. The GPS plots people taped inside trailers turn into timing charts. When the slope breaks at one dome, the second answers hours later, not weeks, and a third basin hums in between. That's coupling on a short fuse. Gases quit whispering. CO2 flux maps that crept outward season by season add new red islands between surveys. Helium ratios lean deeper in basins that weren't on the watch list last quarter. Sulfur remains low until it doesn't. When SO2 finally climbs, it tends to do it late and fast, a sign that caps are fraying, not that magma is just arriving. The moment you smell it broadly, you've crossed a line you wanted days on the near side of. Surface behavior follows suit. Roadbeds that heaved and settled with freeze-thaw start buckling on warm afternoons, the asphalt shingled by uplift along a shallow fracture. Fine cracks appear in boardwalk planks over basins that have been stable since the last rebuild. Lake margins behave wrong. Shore ice forms odd angles, or in summer, the lake level across a small bay sits a few centimeters off what wind and inflow can explain. On Seishi records, you catch a low, repeating oscillation on a windless morning, as if something nudged the basin from below. Meanwhile, the earthquake catalog changes voice. High-frequency popcorn shallow events keep chattering, but the deeper long-period quakes begin to stack in swarms of their own, with emergent onsets and narrow bands, fluid and fractures, not just steam and cracks. Their migration speeds creep toward the middle lane we learned to fear. Faster than poor pressure diffusion, slower than a clean dike, the signature of gas-rich fluids clearing a path while melt pressures the rear. Decision points land without fanfare. First, closures, extra buffer zones around Norris and West Thumb, then full basin cordons when instrumentation shows shallow inflation rates you can't wave away. Next, airspace.
A temporary flight restriction moves from a rectangle over the caldera to a wide oval that covers possible ash columns and drone hazards. The conversations shift from if to how long, and the word indeterminate gets used more than anyone likes. Evacuations don't start with sirens. They start with the people you can move quickly. Backcountry permits canceled. Ranger housing consolidated to safer zones. Contractors told to stand down. Towns get calls that feel like courtesy and aren't. Lodges make contingency lists for buses. Highway crews pre-stage graders and signage to keep routes open if ash falls. Utility managers check with grid operators about load shedding plans and transformer rinse protocols because ash and damp air eat insulators, and you don't want a cascading failure when you can prevent a branch. Sensors sprout everywhere. Spare tilt meters go into shallow holes along ring faults you always meant to cover. Portable gas stations get staked in new meadows that just went brown. Hydrophones drop into West Thumb because if the lake floor starts venting harder, you want to hear it before you see it. Field teams switch from weekly to daily rounds until they're pulled for safety and the drones take over. The monthly blog post is replaced by daily bulletins with graphs that don't hide slopes. Then there's the air. On a compressed countdown, the first ash you meet won't be from a column. It'll be from hydrothermal blasts escalating and vent fields ripping. It's gritty, metallic,
On the tongue, and it travels oddly, streaking the snow or the summer dust in fans you can map with a fingertip. When columns do appear, the first may be modest. A gray stem punching a few kilometers up, sheared by wind, dusting a downwind corridor. That's enough to test airports, enough to test whether jet fuel and ash detectors were more than checklists. If the signs converge, LP stacks, sharp tilts, road heaves, CO2 expansions, sulfur finally breaking through, the window for gentle language closes. You triage choices in hours. Airspace broadens and remains closed. Evacuation rings expand, moving from basins to towns to regions, utilities island sections of the grid to keep hospitals live. Water plants switch to bypass and high-rate filtration because ash clogs screens and baffles. Shelters open farther downwind than anyone planned because wind forecasts are good until they aren't. And ash follows plans the way water does, down the easiest path. This is where training either pays or fumbles. Incident command shifts from the park structure to a unified command with state and federal hooks and titles matter less than who can move trucks. Scientists speak in ranges, not comforts. The phrase "no imminent eruption" disappears, replaced by increased likelihood of eruptive activity and prepare for rapid changes. People complain that it sounds vague. It is. It's also honest. Stakes are simple and stark. Choices made in hours redraw years. Close early, and you take heat for false alarms. Wait, and you trade a comfortable day for a long winter. The old clock promised centuries to breathe. The real one, once it wobbles, demands breath control. Measured, fast, and willing to spend comfort to buy time. Ash, winter, and the web of dependence. Ash doesn't fall like snow. It scratches, it sticks when it's wet, sloughs when it's dry, and finds every filter you forgot to change. In the first days, the plume is the question mark. How high, how fast, which wind? Column height decides reach. 10 kilometers lofted into the jet stream paints states. 20 kilometers laces a continent. 30 starts a story the whole world reads. Winds write the map. The same west to east flow that carries spring storms carries ash corridors over the plains, the Midwest, the Northeast. A day's wind shift redraws the line by 100 miles. On Doppler, it looks like weather. On the ground, it's glass. Airports trace ash advisories, reroute, then shut. Jet engines don't forgive ash. It melts in turbines, coats blades, then rehardens as a glassy glaze that kills lift inside the machine. One test flight in a bad corridor isn't a hiccup. It's a multi-million-dollar mistake and a grounded fleet. Transformers don't like ash either. High-voltage insulators are built to shed rain and dust, not conductive slurries. Add a few millimeters of damp ash and you lower the breakdown voltage. Flashovers arc, substations trip, and grid operators start islanding to keep parts of the system alive. Crews roll with water cannons to rinse equipment, but water is rationed because treatment plants are fighting their own battle. Ash clogs screens, settles in baffles, turns filters into bricks. Some plants go to bypass and boil notices. Others switch to powdered activated carbon and hope the supply chain holds. The micro stories pile up. A hospital chief engineer orders teams onto the roof every 2 hours to sweep intakes and replace filters.
They run out by day 3. An HVAC supplier a state away can't ship because the highway is closed at 3 different points, and the last air cargo hub went dark. A municipal crew learns the hard way that fire hydrants blanket with gray paste when hoses spray, and a ladder company adds brush brooms to its rig. Roads become decisions. Unpaved routes vanish under silt that behaves like talcum. Pavement gets slick in a drizzle, then grinds tires when it dries. Departments of transportation bring out graders like it's a blizzard in July. Plows can push ash, but it doesn't stack well, and drifts into storm drains that weren't built for it. Crews mark intakes with flags, set up vac trucks, and pray. The first real rain doesn't turn everything to concrete. Crops feel it 2 ways, light and lungs. A thin veil in the stratosphere scatters sunlight, cooling afternoons and flattening daily highs. If the column is big and sulfur-rich, you get more than haze. You get a dimmer switch on regional climate. Growing degree days wobble. C4 crops like corn can tolerate some dust, but glass on leaves abrades stomata. Irrigation helps wash it off, if water is available and filters hold. Wheat blades scuff, photosynthesis drops, and harvest crews talk yields in nervous tones. In orchards, fruit sets just as a gritty film settles into blossoms. Honeybee flight windows shrink because they won't work in certain light and temperatures. Pollination misses its mark in quiet percentages that become empty bins. Livestock breathe the same air. Cattle cough eyes.
Tear, and vets warn about rumen issues if ash loads get into feed. Ranchers unroll bales in barns. They usually leave open and burn through winter hay in summer. A supply truck idles outside a co-op that can't process payments because the internet flickers. Someone writes IOU on a grain ticket and hopes the company policy bends. Supply chains don't snap at a single point, they fray. A part you need to fix a plant lives in a warehouse 2 states away, whose forklift runs on a charger in a bay full of ash. Workers are home with kids because school's closed. A regional rail yard slows because brakes don't like glass grit and crews spray everything, then everything takes longer to dry. Cold storage facilities burn diesel to keep temps while the grid blinks. And a nation that doesn't think about compressors learns how quickly a meat plant backs up. Meanwhile, the sky changes moods. Days go jaundiced. Sunsets go theatrical. Nights go colder than they should in August. A farmer steps out and feels the wrong air on his teeth. It tastes like metal. He covers his mouth with a bandana that works for dust and not for this. A week later, he rigs pantyhose over a tractor intake because his grandfather did it once for grasshoppers, and sometimes old tricks are all you have. Communities learn small hacks fast. Tape on door seams. Box fans with furnace filters turned into DIY scrubbers. A shared Slack channel for who has clean N95s. An email chain for which gas stations still have working pumps. A library becomes a cooling and clean air center because its HVAC is newer. A church basement sets up cots in a grid. The first night is calm. The third smells like damp wool and worry. The global piece lands slower and deeper. If the column is big enough, sulfate aerosols climb and spread, reflecting sunlight. Months later, a cool anomaly shows up on seasonal maps. Some harvests move north on timing, others miss by a week. Commodity prices jump, then spike. Nations argue over grain reserves and export bans. The web of dependence we built to be efficient proves brittle. We relearn buffers, we relearn neighbors. Impact isn't cinematic, it's cumulative. Ash is a slow knife on systems that like clean air, clean water, and predictability. In a world built on just in time, a gray film turns in time into too late. Preparation isn't drama, it's friction, on purpose, so the gears don't seize when the air turns to glass. The playbook no one wants to read. Preparation looks boring until the air cuts your throat. Then it's the only story that matters. The playbook doesn't start with heroics, it starts with redundancies, water, power, and comms built to fail gracefully. Cities downstream of the plume draft ash days protocols. Water plants stockpile spare filters and powdered carbon. Rigs for rapid backwash, and portable sedimentation tanks to park next to intake pipes. Reservoirs protect intakes with floating booms and temporary curtains to keep the heaviest load out. Small towns can't afford new plants, so they preload. Extra cartridge filters, bypass plumbing, and diesel for pumps with a clear rotation schedule so fuel doesn't stale when it sits. Power companies write a winter's worth of procedures for a summer week. Substations pre-stage rinse systems, hydrants with foam nozzles turned into ash sprayers.
Insulators get silicone coatings where it's cost-effective. Elsewhere, crews build rinse rotations into 8-hour cycles and bring in night lighting to wash in shifts. Grid operators rehearse islanding plans to keep hospitals and water plants alive, even if transmission stumbles. Backup generators are only backups if they start. Hospitals run them under load monthly, swap oil and filters, and keep spare air filters stacked to the ceiling. Someone prints the checklist because printers die when the internet blinks. Communication plans assume silence. When towers glaze, the net shrinks. Counties issue cheap, simple fixes. Battery-powered radios in every shelter. Ham radio volunteers slotted into incident command like it's 1978. A text tree that runs on low bandwidth and a paper version when bandwidth is gone. Libraries and schools become clean air hubs with upgraded MERV filters and overstocked replacements. Box fan scrubbers, furnace filters duct taped to fans, line gym walls. Not because they're perfect, but because they're fast. And 100 small improvements outpace one perfect plan that arrives late. Food is a different clock. Grocery stores carry 2 days of inventory on a normal week. Ash turns normal into a quiz. Regional warehouses pre-position shelf-stable staples, rice, beans, canned protein, in school cafeterias and church basements within a one-day haul of at-risk towns. Cold storage burns fuel, ration diesel, secure extra, and rotate deliveries during low ash windows. Greenhouses buy time. Cooperative extensions push a crash course in protected cultivation. Plastic hoop houses, shade cloth to blunt diffuse light, and drip lines.
With inline filters so grit doesn't kill emitters. Livestock plans go blunt and local. Cover hay, move animals under roof, stock saline and eye wash, and print vet protocols for ash inhalation when cell service is thin. Healthcare systems plan for lungs. Clinics set up respiratory stations with HEPA units and power strips. Pharmacies build surge caches, albuterol inhalers, steroids, nebulizer kits, N95 size for kids and adults. Home oxygen users get prioritized generator lists, and utilities flag them for early grid triage. Public health prints flyers in 3 languages that say what people actually need. Keep windows shut, put a damp towel under the door, don't drive unless you have to, don't hose ash into storm drains. Fire departments train on dry cleanup. Sweep, bag, lift carefully, because water makes cement. Finance turns dust into rules. Insurance adjusters need standards. When ash counts as direct damage, when cleanup is covered, when a crop loss triggers a payout. State emergency funds set ash thresholds, millimeters on a flat surface over set areas, to release help automatically instead of waiting on case-by-case pleas. Banks pre-authorize emergency credit lines for utilities and co-ops, so purchase orders don't stall when the purchasing officer is sheltering staff. Policy is the hinge. A governor's order can waive weight limits for trucks hauling filters and transformers. A federal declaration can unlock strategic stockpiles, respirators, generators, water bags, and move them by air before towers shut. Customs waivers bring in overseas filter media when domestic stocks vanish. The legal language is the quiet prep. Pre-drafted emergency orders sitting in a folder where the interim deputy knows the password. The drills are where paper becomes muscle. A county runs a volcano winter month on a calendar, not just a brochure. One Saturday, they shut a school's outside air intake to simulate bad AQI, flip the gym into a shelter, and time how long it takes to get cots down, scrubbers running, and a medication table staffed. The next week, water crews practice swapping filter banks while wearing goggles and masks. A grocery co-op rehearses curbside pickup with masks and scripted limits, learning which lines form naturally and where tempers fray. Micro stories mark progress. A diner owner installs a DIY air curtain over the door and keeps the griddle going on a generator. The sign says, "Coffee, bring your mug." A bus driver memorizes a detour that avoids a low spot that drifts with ash. A ranch kid posts a phone video of pantyhose over a tractor intake that saves a day's work. None of this is dramatic, all of it is durable. Preparation meets politics at the budget line. Tourism boards hate warnings. Emergency managers hate euphemisms. The fix is sunlight and mirrors, real-time data portals with raw numbers and plain English captions, independent review boards that meet in public, argue on camera, and publish minority opinions. If you're going to ask a town to close, you owe them the plot, not the headline. In the end, the playbook is friction by design, redundancy,
Buffers, drills, and plain talk slow systems the right way so people don't break when the air does. It won't make ash soft. It will make choices cleaner when the countdown compresses.
The cover-up, or the cushion. Call it two instincts colliding. Shield the public from noise or warn them before the signal screams. Inside the observatory, nobody calls it a cover-up. They call it context. Outside, when updates smooth, sharp edges, it sounds like spin. The truth sits in the tension. Cautious messaging buys order. It also burns time. Start with the basic trade. If you use unrest, you trigger legal thresholds, evacuation planning, closures, cancellations. If you use variability, you keep schools open and bookings intact. Scientists don't control hotel deposits, but they know what a word can do to a town's payroll. A volcanologist once said in a hall, "Our signal is physics, their signal is payroll." That line didn't make the minutes. It framed the next 6 months. There are things scientists can say on the record and things they can only explain in rooms without cameras. On the record, no evidence of imminent eruption. True as far as it goes. Off the record, the coupling is tightening. Lead times shrink when rates lock. That's not a headline, it's a posture. When the two collide, the press gets calm, and local emergency managers get a quiet call to dust plans. The tourism dilemma doesn't wear a villain's face. A county commissioner stares at a spreadsheet that swings with seasons. If a phrase in a federal blog post knocks 20% off summer bookings, his winter road budget vanishes. He's not thinking about melt connectivity, he's thinking about snowplows and payroll. So he pushes the room. Say it's normal. The scientists can't. The communicators split the difference, consistent with past variability, plus a graph that slopes too steeply to be comfortable. Then there are the memos that move like fog. A data embargo justified as quality control keeps CO2 ratios out of a monthly update. Internally, everyone expects the lab to confirm the trend. Externally, the absence of numbers reads as calm. In 3 weeks, the confirmation arrives. The public learns what field crews already knew. Did the delay prevent panic? Maybe. Did it shorten the warning window? Also maybe. A resignation letter that never got sent says the quiet part. Risk communication has been bent by non-scientific incentives. The author deletes the sentence, stays in the job, and sneaks more slope plots into the blog. It's not heroism, it's triage. Most people in these rooms are trying to thread the needle. Tell the truth without breaking things that don't need to break yet. So is it a cover-up or a cushion? The answer is messy. Some smoothing keeps noise from jerking whole regions around. Some smoothing neuters the only advantage we have: time. The fix isn't louder adjectives, it's sunlight and structure. Real-time data mirrors are the first step. Public dashboards that stream raw numbers with plain English captions and links to methods. Not trust us, but watch with us. When you can see tilt steps in near real time, you don't need to wait for a monthly adjective. When CO2 fields expand on the map, you see it the day the field team uploads, not weeks later after a press line is agreed. Add links to live YVO pages and seismic maps so anyone in Denver, Billings, or Chicago can watch the same wiggles the analysts do. Independent review boards are the second step. Panels with no budget strings attached, rotating members from outside agencies, meeting in public with recorded sessions. Put the disagreements on camera. Let the hydrothermal specialist say steam can do this, and let the petrologist answer not at these rates. The minority opinion gets published too. The public learns the shape of uncertainty instead of getting one flattening word. Third, pre-commit to thresholds with pre-written actions. If deformation rate exceeds X across Y stations for Z hours, closures A and B kick in. If long period event density crosses a line in 2 basins, airspace adjusts. If helium ratios trend upward alongside CO2 expansion in specified zones, gas flights cannot be paused by internal review without a countersign from the independent board. Thresholds are guardrails against wishful adjectives. Micro-stories show the value. A ranger at Norris starts carrying a laminated card. AQI thresholds on one side, tilt and quake trigger lines on the other, plus the phone tree that activates closures without a meeting. When the card says act, she acts. She can explain it to a visitor with the card in her hand. It's not drama, it's policy made visible. Ethics land here. Trust is the only early warning system that works. If locals feel sold a slogan, they'll ignore the next one. If they watch the wiggles with you for months, they'll believe you when you say, not today, and move when you say now. That trust costs transparency up front and heat in the middle. It saves minutes on the day they matter. We started with a broken clock.
The fix isn't to shout the hour, it's to show the gears, name the thresholds, and agree on who pulls which.
Liver when the hands stutter. The new timeline, a humble, hard one. We've spent hours with gauges and ghosts. Now put numbers in their place, not as prophecy, but as lanes you can actually drive. Best case first, because people deserve that. The system keeps simmering for decades. Hydrothermal lids fail here and there, craters bite boardwalks, a basin closes for a season, CO2 fields spread in new meadows, and each episode bleeds pressure before melt can organize. The upper reservoir hovers near but below eruptible conditions. Agencies learn to act on thresholds, not adjectives. Tourists still come. Locals adapt to living with ash days that are just steam and mud. It's noisy, it's livable, and crucially, no overdue clock governs this. Recurrence averages are not timers. Plausible case is the one that fits our signals. Decades to a century for the upper reservoir to cross, in patches, into eruptible melt. Not a single switch, but zones flipping, coupling more often, responding faster to deep pulses. You see longer runs of long-period stacks, more coherent tilt steps, gas fields that don't retreat in winter like they used to. You also see policy muscle, real-time dashboards, pre-committed closures, power and water redundancies that turn bad days into hard ones. In that window, a moderate rhyolitic eruption is on the table. Not VEI8 myth, but an event big enough to change maps and seasons in North America for a spell. It's a scale you can plan for if you admit the old overdue myth was a comfort, not a forecast. Worst case is the one the crystals warned about: rapid mobilization within years after a triggering intrusion. A few percent more heat and volatiles slip into a mush that's already closer to mobile than models liked. Thresholds cross quietly, then they fail loudly. The coupling goes from weeks to days. Hydrothermal lids unzip in sequences. A ring fault segment starts to breathe, and sulfur finally arrives everywhere at once. The lead time is real but short. The difference between a scrambled month and a broken year comes down to whether the playbook existed before the slope changed. Unknowns keep us honest. Melt fraction mapping with enough resolution to tell connectivity from volume. Seal integrity along old collapse faults where we've got gaps. External triggers that don't care about our calendar. Regional stress changes, big quakes on neighbors, even seasonal hydrology swings that tweak pore pressures. These aren't plot twists, they're variables. A humble timeline marks them as such and funds the measurements, not the metaphors. So the call for science has to match the risk. More boreholes? Maybe one is enough if we place it where swarms and gases keep drawing the same map. More satellites, definitely. INSAR that sees steps fast, not after a quarter. Gas flights that can't be paused without an outside sign-off. Tomography that resolves melt connectivity in the upper reservoir to the tens of meters we actually need. And money for the boring parts. Filter media stockpiles, spare transformers, regional seed vaults, greenhouse film. This is what a grown-up hazard budget looks like. Here's the hardest sentence. Stop counting from the last big blast like it's a metronome. Start counting from the first coherent rhyme across domains. Gas ratios leaning deep, deformation stepping clean, swarms migrating in trains, crystal clocks that say decades can matter. That's the new clock. It wobbles. It's also the only one that gives you a chance to move. If you want an action list, bookmark YVO's live dashboards, learn local AQI and ash protocols, and ask your city how water and power will ride out a week of grit. We end where we began, at the edge of a decision. Not whether Yellowstone will erupt someday. Whether we choose a timeline humble enough to plan for the decades that matter, and hard enough to hold when the hands start to shake. Resolution and meaning. The clock isn't stopped, it's wobbling. And wobbling clocks are the ones that surprise people who wait for perfect chimes. If you want straight talk grounded in data, stay with us. Subscribe, share this with the person who handles your town's water or grid, and watch the next episode where we pressure test the power system against ash. We'll show the weak links and the fixes that don't need a miracle, just a plan.